So we can talk about these things soon. But for now, let me make sure. Can you all see this page? I'm not sure you can. So can you see the math on the screen?
Yes.
Oh, wonderful. Okay, good. So we're good. Okay, so let me advance the page then. Put in some lines and I think we're off and running. Yep. Okay, so last day of formal instruction, but there's really not any new instruction going to go on today, mostly a review. So some of the important facts, I guess, we're having our final exam 3. This is the final exam, which is the same as our exam 3. Is on December 8th. Now, technically, it's scheduled for 11, but I'm actually starting a little early, 10:30, for those who can start earlier. And we're going till 2:30. 2:30, unfortunately, is the absolute max because I have somewhere I have to be at 2:30. It's a Zoom thing, so I have to go from one Zoom meeting to another. But that should give you 4 hours. I think it should be enough. And for those who can't start at 10:30, then just come at 11. 11 is the normally scheduled time. And that's pretty much that. I'll send you an invitation a little before 10:30, check on attendance, and then just get you started. We had our review yesterday, a lengthy one, actually, as it turns out. I got there a little late, but I stayed well past 5, a little more closer to 6 or 7. And we went over a lot of the problems, didn't get to all of them, but got to most of them. And what I'm thinking of doing is maybe just giving you a list of the answers. To some of the problems that I gave. There are also a few problems that were not on that sample test that you should know. So that's going to be taken care of when I do this review, which I'm about ready to start right now. But I'll try to give you a list of the answers. I'll probably do that in office hours today, either at the end of class if we have time, or office hours, which means right after class. Okay, let me see if there's anything else. Well, there's homework. So I've been getting some questions about where to send the homework and when to send the homework. Let's just make it so you send the homework not on the same day as the 8th. So on the day that follows, it could be the 9th, it could be the 10th. So let's get it in by the end of finals week, I guess. If you really need longer, I probably would take it even longer than that. So if you think that your grades is between 2 grades and you think the homework is going to tilt the balance in your favor, you can even send it in over the weekend. But I'd prefer to have it not on the 8th, something like the 9th or the 10th, or on the weekend. You can just send it to my usual email address, ackrinick.cpp.edu. Okay, try it again. ackrinick@cpp.edu. I'll put that down if anyone still needs it. Matter of fact, even though I wrote it in caps here, I usually write it all in lowercase. I don't think it's sensitive, but you might do it in lowercase. I'm sure that works. That takes care of homework. I don't think I have any other office hours scheduled other than today's. I do have a few sessions scheduled for my other class. They're running a couple days behind you. Their final exam is the 10th, which I think is fine for those few people who happen to have both classes. It gives you time between the classes, so thankfully you don't have it the same day. Any questions about any of this organizational stuff?
Professor, could you give me permission to record when you get a chance?
Sure, I'll do that right now. Is that Alejandro or is that someone else?
Hugo.
Hugo, okay. So let me just see if I can get back to where I need to go. You know, I had it and I blew it. There it is. Hugo, let's see. I did. I gave it to you. Are you okay?
Yeah, I'm good. Thank you.
Let me check a few other people since I'm here. I think a few more came in the meantime. If anyone came in and needs permission, please say something. Okay, caught a couple others. Okay. Any other questions? You could still send me emails after today, and there's things that you're still not sure about. I still meet with people here and there as appointments as needed. So if you're really stuck on some problem, even though I don't have anything formally after today set up, feel free to email me with any questions you may have. Okay, so what's on tap today? Basically a review. Just want to review the topics that you should be prepared for here. And that's it. So let's do the review for the test. Okay, so the material that you're going to be tested on, it's not a cumulative test. It's not, or not comprehensive. It doesn't cover the whole semester. It mainly, the third test is like pretty much the same, similar or to the other two tests. And it covers primarily the last third of the course. So everything that we've done since the last midterm is fair game for this, which is mostly chapter 3 of the book. So what you would expect to see on this test would be questions dealing with Markov processes. Okay, so there will be some carryover topics, but this is primarily what this test will cover, chapter 3, Markov processes. What would some of the carryover topics be? Well, I think an awareness of some of the main results for Markov chains would be helpful because a lot of the results are very similar. So some awareness of Markov chains. Let me give you a few ideas what I'm talking about. So the carryover topics are not the primary topics, but they would be things that you still should know. you should still know, for example, that states are either recurrent and that there are two kinds of recurrent states. There are the no recurrent states. And there are the positive recurrent states. So that situation is still pretty much the same. The difference between these positive recurrent states, so say state I, if the expected, well, first of all, what does it mean to be recurrent? Recurrent would mean probability of going from I back to I is equal to 1. That's recurrent. And then to be positive recurrent, you would need the expected time it takes to first return to I to be finite. That's what positive recurrent is. And null recurrent would mean the expected time it takes to first return to I is infinite. Those are results from chapter 2, but they still hold in the Markov process case. And in addition to recurrent states, of course, there are transient states too. And transient states have where the probability of first going from I back to I eventually is less than 1. Where this is understood that I is an element in the state space. Okay. You should remember that no recurrent states are sort of odd and unusual. They're sort of a rarity. What does that mean? Well, they don't occur, first of all, at all when S is finite. So if you're in a finite state space, you should recall that there are that those states are no recurrent. In finite state space, states are either transient or positive recurrent. So no recurrent states only happen in the setting of when you have an infinite state space. Now that doesn't mean whenever you have an infinite state space, the recurrent states are no recurrent. They may still be positive recurrent, but no recurrence can only occur when there's an infinite state space. So those are topics that you should remember. What else? I think even though they're not going to come up, you still should remember, I think, theorems 5 and 7 in chapter 2. And I'll just quickly mention what each one is. For theorem 5, if you have an irreducible positive recurrent state, then there exists a unique stationary. And the unique stationary at some state I is just 1 over mi. That's again for chains. We're talking about chains here, awareness of chains. And it's a unique stationary. And then theorem 7 says if you have a irreducible positive recurrent aperiodic chain, then this turns into not only the stationary, but the steady state. Okay, so I think the awareness of these two theorems from chapter 2 should still be in your mind. What else? Well, a general feeling of what's going on, I guess. I mean, certainly in a Markov chain, the transient probability matrix, P, the one-step transition matrix, is central. And actually, knowing this, what I'm really trying to get you to know is what holds in the chain, and then how things contrast and look differently for a Markov process. So let's start doing that contrast. I'm trying to think if there's anything else about chains that I may require you to know. Not particularly. So for example, we have formulas for the stationary distributions in chapter 2 for birth disaster chains and for birth death chains. You're not going to see those formulas in this test. You will see formulas for birth, death processes and birth disaster processes. So their analog when you have processes will be on this test. And so when I say keep an awareness of what's going on for chains, part of what I want to stress is there's a difference. We've done a lot of stuff for chains and we redo a lot of it for processes, and you should keep them sorted so that you know. It would be sad, for instance, if you're trying to use even this formula here, which is from chapter 5 and chapter 2 to find the stationary distribution, it would be wrong. There's a counterpart to this formula. How does it look? The counterpart, the one for processes, looks like the same theorem 5. It says that pi I is 1 over qii times what? Mi. And mi in both of these cases is the same. It's the expected time it takes you to go from I back to I. But this is the one that you need to know for processes. So, and this is the one you need to know for chains. This one won't be on the test. This one will. How can you go wrong? If you do this one instead of this one, you'll go wrong, okay? So you have to keep it sorted out. So this would be the counterpart for theorem 5 in chapter 3. And I can show you where it is if you want. Let me see if I can reference it quickly. I'm not sure I know exactly where it is, so it may take me a little bit. In chapter 2, it's theorem 5, but over here in chapter 3, yeah, it occurs on page 103. It doesn't even look like this though, but that's where it occurs, page 103 in chapter 3, equation 49. How does it look? So if you go there, you'll see, well, they don't have i's, they use x, but it's the same idea. They have this, and they put it 1 over qi mi. Again, they use x. And qi for them is negative qii, which is the diagonal entry of the Q matrix. So this is the one you need to know. This one will occur. This one will not occur. Another similar kind of contrast is just the general form. In chapter 2, to find the stationary distribution, you do this. You try to find pi such that pi is what? Pi p. That's how you find the stationary distribution in chapter 2. How do you find the stationary distribution in chapter 3? It's pi times q, and you set it equal to 0. Okay, so this one you're not going to see. This one you will. So these are 2 guarantees. The things I'm circling here are formulas for the stationary distribution. This one comes with some hypotheses. You have to have the irreducible positive recurrent, but then you don't need the aperiodicity in the continuous time case. And then it turns out that the stationary distribution looks like this. You need to know that result. And in general, how do you find the stationary distribution for a Markov process? You solve this equation, which is very similar to solving this one, but it's different. This has a q, this has a p, this has a pi on 2 sides, this doesn't, has a pi over here. So which of the 2 do you need to really remember? The ones I'm circling. And keep this straight so you don't give me these by mistake. That would be sad, because that's going to hurt your exam if you start mixing up chapter 2 stuff with chapter 3. There's a number of things like this, but I'm just giving you a couple of examples so that you can keep things straight. There are results over here in chapter 2, which deal with the birth, disaster chain and birth death chain. In particular, there are equations for the stationary distribution of each of these when it exists. I'm not going to even write them out because you don't need to know that for this test, right? That was tested material on the second midterm. But there are similar formulas. So that, what should I say? Formulas for pi for these guys. You can not worry about those. They're not going to be on the test. But there will be similar formulas over here for the what? For pi in birth, disaster processes. And what? Birth, death processes. For example, the one for birth, death processes is on page 105. And it's given on equation 59 there. And what does it look like? It looks like this. They write it in this notation. I didn't do it exactly as they did it, but it's close enough. We can make use of it. They say it's pi sub x all over something that looks like the summation from y equals 0. They're doing d here. They're doing the finite one, but the infinite one works the same way. Pi y. And let me give it to you in a little more detail. So in a little more detail, it would look like this. Sure, I have this right. It looks like this: 1 plus lambda 0 over v1 plus lambda 0 lambda 1 over mu1 mu2. Keep going. Lambda 0 lambda 1 lambda 2 all over mu1 mu2 mu3. If you're in an infinite birth-death chain, this goes on forever. If you're in a finite one, it comes to a stop after the last state. That's the denominator. The numerator, this part up here, would be, well, in general, it would be this guy, lambda 0, lambda 1, all the way up to lambda x minus 1 all over mu1 u2 all the way to ux. This is what they're calling pi x. This is the formula you need to know. There's something that looks like this involving P's and Q's, which we knew in chapter 2. That's not going to be on this test. This one will, because the test is on chapter 3. This should be memorized. That's on page 105, if you need to refer to it. And they do some examples, I think, right afterwards, if you need to refer to that as well. And there was homework, which, yeah, they do an example right after that. But I think there was homework problems that we did using this. Let me refer to those problems. We did problems 16, 17, and 18. See, homework problems 16, 17, and 18. Okay, those would be examples of using that. That did not occur on the sample test that I handed out last time. And I said I'd come back with some problems. Well, I decided that I don't really need to. I just need to mention this and tell you where the homework problems are that we did. You should look at this formula. You should look at these homework problems. If you have questions, ask me about them right after class. Okay, but this is what you need to know. There's another one. This is for what? This is for birth-death chains. There's another formula like this for birth disaster processes. There's a similar formula. Similar, but different. For birth disaster chains. Not chains, processes, my bad. You should know that one as well. I don't know that off the top of my head, but I know we developed it in class, so I assume it's in your notes. If you can't find it or don't have it in your notes, ask me about it, probably at the end of class or in the office hours. I'm sure someone has it anyway. But you should know that one as well, okay? Why? Because I can give you a question about birth death. Well, birth disaster, yeah. Hope I spelled that right. Yeah. The difference is between disaster and death, right? But anyway, there's another formula for that. And be careful if I'm contrasting chapter 2 and 3. Over here in chapter 2, there was an algorithm. There was an algorithm for what? For finding pi. It was rather complicated. Over here, there's a different algorithm. A different algorithm for finding pi. And remember, over here means we're in processes. You should know this algorithm. You should know how to apply it. I don't have it off the top of my head, but again, you should be able to find it in our notes. It's not in the book. So it's sort of important to get it from our notes. And if you need it, we'll talk about that later. But there's a different algorithm that you would use. It's similar, but actually easier than this one. Okay. So questions thus far? Oh, will there be a question where you need the algorithm? Probably. I'm asking and answering my own questions here. How would a problem like that look? It probably would have more states. And that brings up the other thing you have to be ready for. You need to be ready for your calculator. You have to have some calculator skills here. So calculator, you have to be calculator ready. I'm allowing you to use calculators, but I hope you're able to take advantage of it. You shouldn't be learning how to use the calculator during the test. you should already know how to use the calculator and just make sure you don't make any mistakes. When would you need the calculator? Well, this is one example right here. If I give you a Markov process that has more than 3 states, perhaps like 4, 5, 6 states, that's probably intended to be a calculator problem. Why? Because if you're trying to do this thing by hand for something that has 5 states, for example, that's going to be time consuming. On the calculator, it should be quicker. So you should have your calculator ready to go. If you have a backup calculator, even better. If you need new batteries, put them in before the exam. But you would want to be able to know how to use the algorithm. What else would you need the calculator for? More recently, we needed it for eigenvalues, which I haven't got to yet in this description. But these are two things that you could already anticipate you'll use the calculator for. There's also other things you might want to check your results, and that has to do with multiplying matrices. So you probably want to be able to multiply matrices. Matrices are vectors. So there are uses for the calculator, and you should be ready for them. Questions so far? Okay, if you look on one of those pages, go back and look at the one I was just referring to, 105. 105 has a formula there, 58. So go back on 105, and I've already talked about formula 59. That's this one. That's for birth-death processes, but there's a formula 58, which tells you something really nice. It tells you that a birth-death process is null recurrent. So a birth-death process is null recurrent if and only if two series have to diverge. This one is mu's on top, lambda's on bottom. Summing over S. Well, S in this case is 0 to infinity. Or actually 1 to infinity, they say. Doesn't matter whether you start 0 or 1. This infinite series has to be infinite. And if you flip it over, more or less, why do they say more or less? It's not exactly the same. You have lambda 0 up to lambda n x minus 1. All over mu1 to ux. And you're summing this thing from 1 to infinity. That also has to diverge. They don't prove it, but they state it here, and it's useful and it's helpful when you get to the homework problems later. And this is what you're supposed to be using. These two conditions, if these two conditions hold simultaneously, this series diverges and this one diverges, and you're on an infinite birth-death process, then you've got a null recurrence situation. Remember, if it's irreducible, and that's what we're assuming here, then every state would be null recurrent. Okay, you should know this result. It's similar, again, to stuff we did back in chapter 2, but it's different. How is it different? Back there, it was ratios of what? Q's and P's and P's and Q's. Here it's lambdas and mu's in both places. You're talking about rates rather than probabilities. But what this is a carryover topic. What topic do you have to know? You have to recognize when an infinite series diverges. So you may have to review a little bit of Calc 2, I guess. That's where you do it, which has to do with infinite series, right? When do they converge and when don't they converge? Which ones do you know? If it's a geometric series where the common ratio from one term to the next is less than 1, that converges. When it's greater than 1, that diverges. So if you have a geometric series where what we call R is greater than 1, that will give you an infinite, a divergent infinite series. That's assuming R is positive. Okay. Everything here is positive because these are all positive. Lambdas and mu's are positive numbers. So geometric series, you know when they diverge. There are other series that you learned in calc, things like series for the exponential and sine and cosine. I don't think you'll need sine and cosine because those are negative numbers, but the exponential comes to mind. So you should be aware of what you're trying to do to show it's null recurrent. Will I ask you a question about something being null recurrent? Yes, I did it before in chapter 2. I'm likely to do it again. And I think these problems would be good to look at. They're not on the sample test, but I am telling you about it right now. Okay, I've got somebody coming by my window, so I may not speak for the next minute or two. Okay, they passed. We actually have similar results to this for the birth disaster, which don't occur in the book. I don't think I developed them so much. So I don't think you have to worry about this for the birth disaster, but you do need to worry about the stationary for the birth disaster, which I did do. Okay. What else? So I'm thinking of giving you things, promises now, problems that will be there for sure. So here are some promises. There'll be a small birth, there'll be a small Markov chain. Try it again, a small Markov process. Small meaning what? Maybe 2 to 4 states, more likely 2 to 3. And I'll ask you for pi. If it's what I have in mind here is something that you would be expected to do by hand. There are examples of that sort on the sample test. And of course, that means I want you to use this equation up here. So you have to be familiar with that. And you have to remember that in addition to this equation, it comes with another equation, namely what? Pi 0 plus pi 1 plus, let's say, just say 1 up to pi 2, for example. Then this would have to sum to 1. Don't forget that equation, because if you forget that equation, you won't have enough to figure out what pi is. In other words, pi is a distribution, which means the sum of its values is equal to 1. So I'll ask you to find pi. And once I ask you to find pi, I'll probably follow it up with asking you, that's a stationary. I'll ask you if it's steady state. And pretty much in this case, the answer will be yes, because you don't need periodicity kind of conditions anymore. Don't give me that. That's for chains. For processes, you don't need periodicity. So what do you need for this thing to be a steady state? You need it to be irreducible, and you need it to be what? Positive recurrent states. So you may need this stuff over here. In other words, it won't be a pi when you have no recurrent states. Okay. Okay, and then what's the other thing I could ask you for? I could ask you to find the MIs. And that's making use of this formula up right here. Once you have the stationary distribution, you already know the Q's. So you should be able to solve for the MIs. Okay, this is for sure. If you're not ready for this problem, get ready. you don't get ready, good luck. Because it's going to be there, okay? It's a promise. I'm not saying maybe, I'm saying for sure. There'll be a problem like this, probably 3 states. 2 is too small, 4 is maybe too big, 3 is about right. I'll ask you to find pi, I'll ask you if it's a steady state, and I'll ask you to find mi for some values. Any question on that? 100% sure of seeing this. Not in doubt. What you may also see, and I won't give it 100%, you may see the same question with more than 2 to 4 states on which I'm asking you to use the algorithm. So another possibility would be same type of question. More states. So if you see something that has maybe 4 or 5 or even 6 states, say 4 through 6 states, probably I'm not asking you to do it by hand. I mean, if somebody wants to do it by hand, you can, but I think that's not what I intend. I'm probably asking, I'm going to be asking for pi again, and I'm thinking you're going to use the algorithm. I'll ask for pi again. I'm thinking the algorithm. Same kind of questions. Is it the steady state and mi? Mi. How likely it is you'll see this question? At least 80% chance. So, I mean, if someone's telling you there's at least an 80% chance of it coming, you should be ready. What am I saying? Be able to use the algorithm, be able to use the calculator. Otherwise, this is going to take a long time. Okay, so those are 2 promises. I could ask the same kind of questions for a birth disaster. Well, so let's no, actually, let's not go to birth disaster. Let's go to birth death first. Same kind of questions. We could ask it for birth, death processes. In particular, birth death processes that have what? An infinite number of states. It's a similar kind of setup, but this has only 2 to 4 states. This has, what did I say, 4 to 6 states. So this is intended for the algorithm. And if you have an infinite number of states, then you're intended to use this, right? If I find, if I give you what the lambdas and the mu's are, and I ask you for the stationary, I'm really testing, do you know how to use this formula, put in everything, recognize what the infinite sum is on the bottom, assuming it converges, and giving me the stationary distribution. So same kind of question, but for birth death with infinite number of states. How likely is it you'll see this? I'd say at least 80% chance. So let's be clear. In this thing, I'm not expecting you to do it by hand. I'm not expecting you to do it by algorithm. I'm expecting you to do it by memory using this formula. If you don't know this formula, next problem, right? You're done. You can't do it. But if you know this, hopefully you'll be able to nail down what everything is. And then I could have the normal follow-up questions of, is it a steady state and mi again? So all these follow-ups are still similar. Steady state. And what about mi? Okay, so these are all similar kind of problems, just different states or different settings with different processes. With this last one in mind, if I want to become a little, push the envelope a little bit, I could ask you to do it for the birth disaster case. Assuming we have an infinite number of states again. infinite number of states. What you would need is something that looks like this, but for the birth disaster. We actually did that in class. Okay, we actually developed what the stationary distribution would look like. I don't have it off the top of my head, but you should have it in your notes, and if you need to, we could talk about it later. But again, it would be, I'd say there's a decent chance of this. I don't know if I'd put it as high as 80%, but there's another chance here. I could ask you for both of these guys. Okay, so let me put this at say 70% chance. Still, that's still quite high. 70% chance. Means what? Means you should learn the formula for this, even though I'm not giving it to you off the top of my head. What else could I ask? I could ask you to prove these formulas. Proofs of the formulas. We did them both in class. It was sort of cool because you had an infinite number of values there, but we were able to solve this thing. Even though we had an infinite number of values here, proof of these formulas. What's the chance of seeing either one of these and it asks you to prove it? I would say, well, I would say these are some of the formulas you should know in terms of proofs. So normally I give you about 4 or 5 proofs and say that 2 or 3 of them will be on the test. I would say knowing the proof of the stationary for this and the stationary for that would be 2 of the proofs you should know. So I won't say what the percentage chance is that I'm going to ask you to get that proof, but these are 2 proofs you should know. 2 proofs of formulas you should know. One of them is right out of the book, the birth disaster we did in class, and that's not out of the book. Okay, so now I've given you 2 proofs you should know, and I've given you 4 problems that are highly likely to occur. Any questions thus far?
I had a question about the proofs we should know. You mentioned before you might put the proof for the algorithm since it was shorter than the other algorithm we use for Markov chain. Would that be a possibility?
That would be another one. Thank you. Yeah, so let's fill that out too. And by the way, I haven't thought about that proof lately, but I know I did it in class. I'm not even sure it was a proof. It was an explanation really, right? Because there was one part there where you had to assume the inverse exists. But yes, the explanation of the algorithm. So now we've got 3. These are 2 different proofs of finding stationary, and this is explanation of the algorithm, just what we developed in class. And to be honest, I don't remember this myself at the moment, but the approach, I'm sure we can come up with it. Thank you. So we've got 3 proofs now that could be there. Probably I'll give you another 1 or 2, and that'll be it for proofs or explanations. What else? Well, okay, the big stuff. So the stuff we've been doing recently. Well, okay, here's another proof. Explain properties of P. Try again, properties of Q. So Q has 3 properties. The rows add up to 0. The off-diagonal elements are non-negative. The diagonal elements are non-positive. Why do those properties hold? We gave an explanation in class. Know the explanation. Okay, so now we've got 4 proofs to know. 1 for each of these, the algorithm, and now explaining the properties of Q. This one I know I can give off the top of my head, so if we need to, we can go to that quickly. But where I wanted to go is the other thing we've been doing is so this deals with trying to find the steady state and stationary. But the other big topic is to find what? Find P of T. What is P of T? Well, the easiest case is the 2x2. And this is finding the probability of going from one state to another in time t. Those are functions, probability transition functions. And that's more difficult than finding stationary or steady state. Stationary or steady state, there are formulas. To actually find this stuff, you need to do the forward and backward equations. So you need to know those. The forward and backward differential equations, which are looking like this. The backward looks like Q times P of T. The forward looks like P of T times Q. It turns out they're both true. I could ask you to prove this, but I doubt I will do that. That would be using Chapman-Kolmogorov equations, and I doubt I'll go there. But you still should know the results. Okay, what do we usually do? To find these guys, you have to solve these equations. There's two ways to go. So now we're solving a system of linear differential equations. And that was a sharp turn in what we did before. We weren't solving systems of differential equations until we got to the continuous case in chapter 3. So what are our two methods? Our two methods were separation of variables . These are methods not of probability of solving differential equations. And the second one was how to solve a linear constant coefficient differential equation. Separation of variables, I think you know, I hope. That's the easier technique. But the second technique is done on page 92. So for the second technique, see page 92, equation, I think it's toward the bottom of the page. Well, actually, equation 23 would work. I don't have time to go through that in detail, but we have used that a couple times. Okay. The easiest example of this I can give you is what's right on the board right now, would be the 2x2 case. But this is not easy. If you're just trying to solve that using these two methods, that was done on page 93 and 94. So this case was done on page 93 and 94. They do it in the general case where Q looks like what? Lambda minus lambda mu minus mu. And the formulas are quite, they're a little lengthy. Their formulas 27 through 30. So the answers are formulas 27 through 30. Would I ask you to do that? Maybe. I'd say there's a 50-50 chance of that. So let me say at least 50% chance. I might just put numbers in here and ask you to do it. I think that's what I did on the sample test. Okay. Why is the probability only 50%? Because it's really an exercise in differential equations, which is okay, but you have to know how to manipulate the equations appropriately to get these answers that are given on the answers are back here on 27 to 30. And by the way, well, I'll just give one of the answers so we get the feel. So P00 turns out to be mu over lambda plus mu plus lambda over lambda plus mu e to the minus lambda plus mu t. So this turns out to be the equation for P00T. So they're rather complicated, but they do involve a constant term here in terms of lambdas and mu's and an exponential decay function. They all have this kind of form. Okay, so if you want to be ready for this one, review page 93, 94. We did this in class as well. I followed the book's explanation very closely. So my explanation in the books was pretty much the same here. Okay, but that's for the 2x2. And why is it as high as 50%? Because this is the easiest non-trivial problem, okay? And this will take some time. And if you look on this page, these pages, you see it's sort of tricky. You have to pick the right equations to add and subtract and get it to work. But then we have more recently this past week, we've been doing this not using differential equations. We've been using this equation. So an alternative way of doing the same problem, let me just put it that way, would be writing it this way. A1 e to the omega 1 t plus a2 e to the omega 2t. So this is giving you a result that a matrix like this can be always written in terms of exponential functions of its eigenvalues. This is omega 1 and omega 2 are distinct eigenvalues. And the A's are constant matrices. A1 and A2 are constant matrices. So this starts with this result. And what that means is the work for finding the solving the equations has been done. The only thing you need to do is figure out what all these constants are. So you need to be able to figure out its eigenvalues. It's the distinct eigenvalues of what? Of the matrix Q. So you have to have your hands on the Q matrix here. And for that, it's only two, you can just do it by hand. But if you were to have more than two eigenvalues, there'd be more than two terms here. And then you probably need the calculator to find the eigenvalues. And then once you have the eigenvalues, then it's a matter of figuring out these coefficients. And you figure out these coefficients by taking derivatives of this, setting t equal to 0, and forming equations involving the A's. It's a little complicated, so I don't have time to go over that in detail, but we've done enough of it that I hope you could be able to do it. And if you do that, that's a different way to get this formula over here if you did it for the two-state guy. The nice thing about this is it works not only for the two-state guy, but when you have three states, like what? Like I'm confident we could do homework problem number 2 at the back of the book using this method, except you'd have one more term because you have 3 states there. You should look at homework problem 2. There's one on the sample test that looks very similar to homework problem 2. So I would say there's a good probability that I'll give you this kind of problem, which is to find P of t. Probably, high probability. What does high probability mean? I'd say 80% or higher. To use this result for a what? 3x3 case. 3x3 is a little more complicated than 2x2. You're finding 9 things rather than 4. But it comes down to getting the eigenvalues. By the way, one of the eigenvalues is always 0. So in the 3x3 case, even if you don't know how to do the calculator, you can find the characteristic polynomial. You can factor out one of the eigenvalues to be 0, and you can solve the other two by the quadratic equation. So the 3x3 case, you could actually do by hand if you get stuck. You know what you're doing. Anyway, there's a high probability I'll ask you to do one of these. I could ask you for the 2x2 case or 3x3. That's probably where I'll draw the line. Now, and there's over an 80% chance of this. 80% or higher that you'll see one of these. And if you look at the sample test, there's like 2 or 3 of these on the sample test, at least 2. So, so when I say there's a high probability, if I really want to see this, I'll tell you what I could ask. I'd ask you to do the 2-state, figuring that's the easiest one, and you already have the answer the other way. And then maybe ask you to do a 3-state as well. I even got very creative. I didn't realize how creative until yesterday when I had to solve this problem. So I'll just mention this because where the review left off yesterday was sort of interesting. I gave this diagram. That's a 3-state, rather simple diagram. And I'm not sure what I asked for. I think I asked for P00T. I think that's what I asked for. So I just asked for one of them. And it's a rather innocuous looking problem. It looks like it should be not hard to do. But it turns out it is more, it's different and harder than probably what we've done, because we haven't done anything quite like that, as it turns out. Can you use this method here? Yes. Can you use the method above where you're actually messing with differential equations and using separation of variables? I don't know. I mean, I'm confident probably that works, but I didn't try it that way. I tried it this way. And there's a twist. When you try it this way, the eigenvalues turn out to be complex. Complex number eigenvalues. So that was a little surprise from yesterday. It turns out that this formula works anyway, even with complex eigenvalues, provided the eigenvalues are distinct. However, the matrices also have complex numbers, which means it's really an interesting problem. The eigenvalues are complex, the matrices are complex. There's a third one here, so I'm trying not to, if I were to refer to this, there would be a third term, A3, e to the, well, the eigenvalue of the third one would be 0, so it would just be this. A1, A2, A3. It turns out that these guys are complex eigenvalues. In the matrices, they're complex numbers. And what makes it pretty cool is all those complex numbers, when you combine them, give you this matrix, which is real. So P00 is not complex. All the complex parts cancel out, and you just end up with the right thing. You won't see that on your test. So you can breathe a sigh of relief. Basically, I'll tell you the answer, just for those who are curious and were there yesterday, because I didn't get to that one. That was at the end of a long session. But just to let you know what gives, let me see where, somewhere I have the answer. Yeah, it turns out the answer is this, for those who have some interest. Turns out that the answer is 2/3 e to the minus 2/3 t, or e to the minus 3/2 t rather, cosine the square root of 3t all over 2 plus 1/3. Okay, so the good news is you're not going to see this, and I'm not going to give you anything that has complex eigenvalues on the test. But just to finish the class on a on the high point as far as what goes on, it still works. This method still works, and I presume this method works if you actually know what you're doing. So somehow you'd be able to get this from this. I'm not quite sure how there, but I know how to get this one. And the thing that's of interest, just on the side, this is an example. So far, all the examples of P's have involved exponential decays in a constant. A cosine sneaks into this, trig function sneaks in. And you could actually, with complex variables, have a sine sneak in. So the answers in general could be exponential decay functions and sines and cosines. When do you get the sines and cosines? Pretty much when you have complex eigenvalues. So you should not come up with something like this on Wednesday. Okay, I think I'm done. Let me make sure I haven't forgotten anything. Out of time. Have I given you enough proofs to know by heart? So I've asked you to know how to prove the stationary for each of these. That's 2. I've asked you to explain the algorithm. That's 3. I've asked you to explain the properties of Q. That's 4. I've sort of hinted that I could give you the 2x2 case, and you might think of that as memorizing a proof. So that could be 5. So I'm asking you to know like those 5 proofs. And then know a lot of formulas. Oh, what I've left out are counterexamples. So, okay, so what's left out should have included. This is not there. Not on our test. Which is pretty weird because this is pretty simple looking. But it does involve complex numbers. What else should you know? You should know definitions. You should know examples. You should know counterexamples. So going back to midterm 2. In midterm 2, I asked you for an example in the birth disaster chain of a no recurrence system. And then I later asked you for an example on a birth death chain of a no recurrence system. Those questions were straight memory. I expected you to memorize those counterexamples. The one for the birth disaster was harder, but the one for the birth death turned out just to be what? Just having 1/2 top and bottom everywhere. And that was sort of, you got it or you didn't. You either remember the example that was no recurrent or you didn't. I could ask similar counterexamples now for processes. So can you give me a birth death process that has no recurrent states? And I think the same idea works here. So instead of it being 1/2, if you wanted just to make it rates, I'm pretty confident that if you were going up with rate 2 and going down with rate 2, I believe that everything here is now recurrent then. That's in the birth disaster process. For the birth, that's for the birth death process. For the birth disaster process, I think it would be harder to come up with one. We didn't go there. But there are things like that that we've done along the way. So examples, counterexamples, definitions. You know, if I were to ask you, here's one. What's the Markov property for Markov processes? Could you figure it out? Could you write it out? What's the Markov property? That's just like, do you know that property or don't you? Well, now that I tipped you off, I hope you will. What does it look like? It looks similar to the one that we did in class. It's this thing. If you want it, if you know what it is at time 0, you know what state you're in. And you know what state you are in at time 1. And you keep going up to time n. I should put the times in parentheses, sorry. All right, so my notation is off. Idea is right. So at time 0, you're at state I0, and at time 1, you're at state I1. Keep going up to the time n, you're at state In. And you're trying to find the probability that at time n plus 1, you're at state what? N plus 1? The Markov property says that this conditional probability collapses and just becomes this. You can cancel all this stuff and you just get the most recent time. So that's the Markov property, but it has to hold for what? For all T0 less than T1 less than T2, all the way up to Tn plus 1, so all times n for all n. In other words, this messy conditional probability can be simplified. You can cancel out all the distant past, just keep the recent past. And it's the same as this conditional probability. That's the Markov property. It's pretty much what it was in chapter 1 and 2, but it's now got times instead of integer times. All these t's could be anything, right? T1, T2, up to Tn plus 1 could be anything in the interval 0 to 30. Okay, so that would be a straight definition. All right, I'm out of time. Questions though. So questions on the review. Do you have a good idea what this thing's going to be about?
I have a quick question about a null recurrent birth-death process.
Please.
So as long as the rates are the same everywhere, then it's null recurrent?
I think so.
Okay.
Yeah, I think so. And I think we could actually prove it from these conditions right here.
Okay.
Which got a little erased, but they're sort of there. Because if the lambdas and the mu's are the same, then you're just adding up 1 infinitely often. And that's going to be infinity, and the same is true here. So if the lambdas and the mu's are the same, all the same, say, then this should work. There are other times, there are other examples, but again, that would be a full explanation. If I just said, give me an example, then the example would just be something like this. It keeps on going like that though, right? And if you wanted more, if I wanted more of an explanation, you can just give this result up here. Other questions? Okay, let me take 20 or 30 seconds to catch my breath and turn to any problems you may have. I assume that this problem came up in the last time I taught the class, and that's why I put it on the test. And I'm not putting it on the test because you can see that we didn't talk about complex eigenvalues at all until this problem came up. But I'm okay. At least you know it could have happened. And even though I'm not going to test it, I'm still glad it sort of came up, even though it's a curveball. Okay, let me take some water. Yeah. I'll be right back. Gotta get some water. Okay, I'm happy to answer questions either on the review or any homework problems or sample test problems that you'd like. Oh, I also said I'm happy to give you the answers on the sample test. I could do that.
Hey, Professor, I have a couple questions.
Sure, go for it.
So I know we briefly went over the stationary distribution for a birth disaster process, but
Right,
you left it for homework for us to find it,
okay,
and I wasn't able to work it out on my own.
okay, let's do that one. So birth disaster process to find the stationary, right?
Yeah.
Sounds fine. And let me just see if there are other questions too. Anyone else have other questions? Yeah, so anything that like that, that's a perfect question. Anything that we assigned for homework and I indicated you should know, like in the review, and we didn't go over it or you got stuck or whatever, that's a perfect kind of question to ask right now.
Would you be able to go over number 17 on the homework?
Sure. So I've got this and I've got number 17 on chapter 3, I assume. Anything else?
Can we go for number 2 from chapter 3?
Oh, okay, number 2. That may take a little longer, but that's fair game. Okay. We have different ways to do it now. At least one way should be relatively routine. Okay, anything else? Okay. Let's do the birth, the birth, well, that looks like it's birth disaster, right? Let's do the birth disaster one. I thought I did it, to be honest, but if not, that's fine. Let me just turn the page and do that. And 17 and 2. All right, so that should work out. And all answers, okay. So remind me to do all the answers. That'll probably take 5 minutes to list. So, clean page. Too many, too much. There it is. Okay. Good, good. So birth disaster. Birth disaster looks like this. Going up with rates, let's say lambda 0, lambda 1, lambda 2, etc. Going down, rate mu1, but here it would be what? mu2. Here it would be mu3, and etc. So there, the next day would be 4. You go up with lambda 3 and down with mu4. So the pattern persists. What are we after? We're after the stationary distribution. So we want pi. It's found by doing this. Okay, so we need to know what Q is. So Q from 0 to 1 is lambda naught. You can't get to 2 from 0 or 3 or any of the other states, but 0 to 0 would have a rate being minus lambda naught because the sum of the rows must add up to 0. So that's the first row of the Q matrix. What's the second row? From 1, you can go to 0 with rate mu1. From 1, you can't go back to it. Well, don't worry about coming back to itself. We'll do that later. But from 1, you can go to 2 with rate lambda 1. From one, you can't go to anywhere else in one step, so the rest are all zeros. And this would have to be minus the sum, so that it adds up, each row adds up to 0. So that's row 2. So far, so good. Getting the Q matrix is important. If you don't have the Q matrix, it's not going to work. Okay, from 2. Well, from 2, you can go to 0 with rate mu2. You can't get to 1. Yeah, getting to 2 we do at the end, but from 2 to 3 is lambda 2. So that's where 2 to 0, 2 to 1, 2 to 2, 2 to 3 is lambda 3, right? No, lambda 2 for the read my own writing. And then from 2, you can't get anywhere else. 0 the rest of the ways. This guy keeps disappearing. And then this guy would be what? Minus the sum of these. And that's the pattern. So if we wanted to go one more, we could see how it would look. It would be mu3 here. There would be 2 zeros here. There would be something that we fill in here, but this would be lambda 3, and then this would be minus the sum of those, lambda 3 plus mu3. And there would be zeros the rest of the way, and so it goes on forever. Questions about the Q matrix? That describes the transitions in this birth disaster process. Okay, now we're visualizing. Take this thing. Let me be a little lazy. Take this matrix and multiply it on its left by pi 0, pi 1, pi 2, etc. And set it equal to what? All zeros? That's what this equation says to do. Okay, from experience, I'm not going to multiply this row times this column because it's depressing, it doesn't lead to anything. So I'm just going to go for the second one, and that's just because I've been here before. If I multiply this vector times the second column, what do you get? You get pi 0 times lambda 0 plus pi 1. Well, it's actually minus because it's going to be this. I'll write it that way. Times what? Lambda 1 plus u1. And then all the rest are zeros. And what's on the other side? 0. So what did I do? I multiplied this row vector by this column vector. The only contributions I get are from the first two terms. This times this and this times this gives me this stuff. Everything else would give me 0 because there's all zeros on the rest of the way here. So this is my first equation. And then I do the same thing by multiplying this row by the third column. And if we do that, what do you get? Pi 0, 0 times 0 disappears, but you get pi 1 times what? Lambda 1. And then you get pi 2 times this stuff, lambda 2 plus mu2. And then all the rest are zeros. So the pattern is becoming clearer. Let's just do one more. So if we multiply this by what? The third, no, we did this times this, so that was this one. We did this times this, so that was this one. So now we have to do this times the fourth column. So we know it's going to be on the left, it's going to be 0. But when we multiply this row vector times the fourth column, the first two entries go away because of these zeros. The first entry that doesn't go away would be pi 2 times lambda 2. And then the next entry would be what? minus pi 3 times what? This guy, which is what? Lambda 3 plus mu 3. And I'm assuming, yeah, everything else will be 0. So that's that. Okay, so that's the pattern. Now, here's the rest of this, and it finishes fairly quickly. From the first equation, you can solve for pi 1 in terms of pi 0. So how would you do that? You can just bring the pi 1 term to the other side. So you'd have pi 1 times lambda 1 plus mu 1. And that would be equal to what? Pi 0 times lambda 0. And if you want now, we could then divide by lambda 1 plus mu 1. So pi 1 would be, let's write it in a different order, put the lambda 0 first, put this on the bottom, lambda 1 plus mu 1, and all of that times what? Pi 0. So this is important. Why? Because it tells you what pi 1 is in terms of pi 0. Let's make sure I did it right. Bring this to the other side, solve for pi 1. Yep, I think it's okay. So let me put it on the box. Do the same thing for the second equation. So for the second equation, which is this one, swing this to the other side. So that would be pi 2 times lambda 2 plus mu 2 is equal to what's left, which is what? Let's put the lambda 1 first. Lambda 1 pi 1. Yep. And now solve for pi 2. So divide both sides by lambda 2 plus mu 2. So pi 2 would be lambda 1 all over lambda 2 plus mu 2 times pi 1. Throw that in a box. The pattern should be clear now. Let's do it in general. So pi n would be lambda n minus 1, just looking at the pattern. And then it should be lambda n plus mu n. And this would be what? Pi n minus 1. So this seems to be what holds in general, starting at 1. So n equal 1, 2, etc. Are we together? Everyone okay?
Yeah.
Good. Okay, so, but from this one, we can extend it a little bit. So it's lambda 1 over lambda 2 plus mu 2. Pi 1, but pi 1 is this. So if I substitute pi 1 into this, I'll get this times lambda 0 over what? Lambda 1 plus mu 1, pi 0. See what I'm doing? I'm getting pi 2 now in terms of pi 0 by combining these two equations. For pi 1, I'm putting this in, which I did here. And so I got this. Okay, so can we see the pattern in general? Hopefully. Let's see. So I think in general, what we can say is pi n will look like the start will be the same, lambda 1 over lambda 2 plus mu 2. And then, well, I got actually I should already do that. It's when this was 2, this was 1 less. So this should be lambda n minus 1. And this should be the same as this. So it would be pi n, it would be lambda. I'm just doing the pattern here. Lambda n mu n which sort of expresses what's going on, whatever the index, this becomes the index of the bottom and one less on top. And then this would be pi n minus 1, but we know how those look. So it would just continue looking like this, where all of the indices are one less, lambda n minus 2. And this would be lambda n minus 1 plus mu n minus 1. And so you would go until you work your way down to this guy. Okay, this is sort of important. So I'm noticing a pattern, and this holds starting when n is 1, I guess. Yeah, it starts when n is 1. So this would be a formula from 1 to all the way up. Okay. Does everyone see how I'm getting this? I mean, it's sort of done here for pi 2. Pi 2 is this times pi 0. And so I'm generalizing that. I'm replacing 2 by n. And I'm saying the indices here would be 1 less on top and the same as n on the bottom. Then the next one over is 1 less than this. And these would be 1 more than this one. And that pattern persists until you get to the end, which is this. Okay, so what can you say now? If you remember that pi 0 plus pi 1 plus pi 2 all the way out to infinity equals 1, then pi 0 is itself, that's fine. But pi 1 is equal to this stuff, lambda 0 over mu, lambda 0 all over lambda 1 plus mu 1, I think, times pi 0. Let's make sure. Yeah, that's this. And pi 2 would be this product. So it would go lambda 1 over lambda 2 plus mu 2, lambda 0, lambda 1 plus mu 1 times pi 0, and so on. And you can write in the so on parts with this, okay? And the cool thing is you could now factor out the pi 0. So pi 0 is 1 plus lambda 0 over lambda 1 plus mu 1 plus this stuff, lambda 1 over lambda 2 plus mu 2, lambda 0 over lambda 1 plus mu 1, and so on forever. And now you can solve for pi 0. So what's pi 0? So pi 0 would be 1 over this infinite sum. Let me just call this, well, all right, I'll write it again. 1 plus lambda 0 over lambda 1 plus mu 1 plus lambda 1 over lambda 2 plus mu 2 times lambda 0 over lambda 1 plus mu 1. And, you know, the next one, just so it's clear that we understand what we're doing, lambda 2 over what? Lambda 3 plus mu 3. And then the rest would be the product of these things. Lambda 1, lambda 2 plus mu 2. And then lambda 0, lambda 1 plus mu 1. And so forth. So this would be pi 0. And it only makes sense provided, let's call the sum on the bottom S. It only makes sense provided S is finite. Because if this, lambdas and mu's are all positive. So this is an infinite series of positive terms. And if it keeps going, getting bigger and bigger, if it doesn't converge, then it goes off to infinity because everything, you're always adding positive terms. And if it goes off to infinity, then you have pi 0 being 1 over infinity, which is 0. And once pi 0 is 0, then all the others are 0 because of this. And then they can't add up to 1. So this only gives you the stationary distribution, provided this infinite series on the bottom is finite. Another way of saying it is the stationary, so the stationary will exist provided this infinite series is finite. And that means when it's finite, okay, what I'm trying to say is this will also be the condition for it being positive recurrent, right? Because it'll have a stationary distribution if it's positive recurrent, and it only has a stationary distribution if the sum is finite. So if the sum turned out to be infinite, then it would not be positive recurrent. What does that mean? It's either a transient process or it's a no recurrent one. But if you want to know when stationarity occurs, this is the condition. And what do the pi's look like? In general, pi n, well, that could be found by this expression up here. So you just put this up top and so it's all this starting at n-1, I guess. Lambda of n-1. In the bottom, everything is bigger. All of this, and then n-2. Until you work your way down to the last guy, which is this, lambda 0. All over lambda 1 plus mu1. And then that's all over this infinite series again. So if you want to just call it S, that would be convenient. So this is the formula for pi n. And that works actually, well, this one works whenever n is what? 1 or bigger. At 1, you just get this guy over S. And for 0, it's this. So the formulas, these would be the two formulas for the stationary distribution. This is not that different than how the proof for the birth-death one works either. In other words, this whole method of writing out the matrix, and you skip the first product because that's depressing. It gives you an infinite mess. But all the other ones are nice because all the other columns have only 2 non-zero values. So it just picks off 2 of these guys. And then there's this pattern. Questions?
So then what are the conditions for it being null recurrent or transient after the sum diverges?
If you already know, I think you'd have to go through, okay, so let's just say what we've got in front of us. What we have in front of us is a condition for when the stationary exists. The stationary distribution exists provided this infinite series on the bottom converges, okay? Now, so theorem 5 updated to chapter 3 would say that this will only give you will only have a stationary distribution. If it's transient, you don't have a stationary distribution. So basically this series converging is telling you when it's positive recurrent. So if this series converges, then it's not transient. Why? Because if it was transient, you wouldn't have a stationary distribution at all. It would be going off to infinity. And it's not null recurrent. So you actually, so what you have is it's positive recurrent if and only if this series converges. Now, what you would also need, so So what you would need is a companion result. If you want to know when it's null recurrent, which I think is what you're asking, you would want it to be not transient, and yet the series would go off to infinity. So here's a partial answer to your question. For a birth disaster process to be null recurrent, you need this series to be finite, but that's not enough. And you need the process not to be null recurrent. You need this to be infinite. I have that wrong. Sorry. You need this to be infinite, and you need the process not to be transient. So you would have to come up with a condition of when this process is transient or not. And how would that work? I don't know if I want to spend the time, but let me see if I can at least give you a feel for how that would work. Since everything is irreducible here, it would be coming down to saying you want to find out when row 0, 0 is less than 1. Because when row 0, 0 is less than 1, that makes 0 transient, and 0 communicates with everything else, so everything else would be transient. So that would give you, if you can develop a condition for this to be true, then whatever that condition is, you'd want that condition not to be true as well. So how would row 0, 0 being less than 1 look in this scheme? Let's see if I can at least answer that a little bit. Go back to my picture, wherever it is. Yeah. So I think the short answer, which is what I need at this point, would be do the condition that we had in chapter 2 for it being transient. So in chapter 2, all the lambdas were p's and all the mu's were q's. And we actually figured out, I'm not sure we did it, but I think we did it. Chapter 2, I'd have to think about. We could actually figure out what it, yeah, so here's the short answer. Figure out what this means when it was a chain. So if it was a chain, then these would all be P's, these would all be Q's. And then the chance of coming back in one step would be the loop, whatever that would be. So if this were P0, that would be 1 minus P0. That would be coming back in one step. 1 minus P0. And if you came back in 2 steps for the first time, what would that be? That would be P0Q, it would be P0Q1 plus P0Q1. And coming back for the first time in 3 steps would be what? Would be P0, P1, Q2. P0, P0, what did I just say? P1, Q2, I think. And that would be the pattern. P0, P1, P2, Q3. And if you, so this would be coming back in 1 step, 2 steps, 3 steps, 4 steps. That's the only way things can happen because of the nature of the transitions. So if you're going to come back in n steps, you really got to go up here to n-1 state and then go shoot down. That's the only way to get back in that many steps. Okay. So what you would want for, if it were a chain, you would want this to be summing up to less than 1. If it's summed up to less than 1, then 0 would be transient. And what I'm suggesting is, so what does that come down to? It comes down to an infinite series that really looks, this is a little, the loop is a little unusual, but if you just concentrate on this part of it here, that has a pattern. And the pattern is just multiplied by the amount of p's and then have the q at the end. So what I'm suggesting is if everything became a process, it would be a similar pattern. So this would be lambda 0, u1. This would be lambda 0, lambda 1, u2, lambda 0, lambda 1, lambda 2, u3. So I'm saying by analogy that you'd want this to be less than that. Okay, so this is what you need. If this happens, then 0 is transient and so are the other states. So if you want it to be transient, you'd have to have this. And if you don't want it to be transient, and you want it to be recurrent, then you'd have to have this series be equal to, well, I guess all of that with this one too. All right. So I guess this would be 1 minus, what is it? Lambda 0, whatever. So if all of this equaled 1, that would correspond to 0 being recurrent. So you would mean that, so that would be what you need. You would need this series to converge to 1. Let's make sure I'm doing that right. Yeah, because if it converges to less than 1, then it will be transient. So if it doesn't converge to less than 1, if it converges to 1, then it'll be recurrent. So I think this is the condition you need. You need this infinite series to be recurrent. You would need this series here. 1 minus lambda plus lambda 0 u1 plus all of this. To equal 1. That's to be recurrent. So you need this condition to hold for recurrence. And then you need this thing to be infinite. And if both of those conditions hold, then you have it being null recurrent, which is what I think you're asking for. I wouldn't worry about this part though. What I would be more worried about is the part I did before your question. Yeah.
Okay. Yeah, because I was just wondering, because like these rates can, like the lambdas and mu's can be above 1 as well, greater than 1. So
Yeah. So yeah. Let me think about that. So is the analogy work? So maybe. Yeah. So maybe this is too much by analogy. I'm doing the analogy with the chain, right? And I'm replacing the probabilities with the rates. So okay, then let me just go to where I was anyway. It would be something along these lines, but I'm not sure this is correct. But I'd say don't worry about it. Okay, in terms of the test. In terms of the test, what you need to know is what's in the boxes here.
okay, sounds good.
Yeah. So I'd have to think a little more clearly. Thank you, though. Okay, let's move to the other problem. The other problem was 2 and 17. I think 17 may be faster, so let's do that one first. So it was 17, right? Yeah, all right, so what does 17 look like? So 17 says, suppose you have a birth-death process on the non-negative integers where lambdas and mu's are positive. And you set gamma 0 equal to 1 and gamma of this stuff to be this. Show that if the sum of the gammas is infinite, then rho x0 and then rho x0 is equal to 1. And show that if the sum of this infinite series, same infinite series, is finite, then rho x0 equals this. And in that case, it'll be less than 1. Okay. So, all right. And then it gives you a hint. Use exercise 26 of chapter 1. I think the hint's a good one. So let's look at 26 of chapter 1. Okay, so this is very similar to what I was just being asked about. It's something that we already proved back in there for chains. And they're saying extended to processes, basically. Let me see. I think I just did this by, yeah, just by taking something out. Give me a second here. I think what I did before, and I think I did this before, by the way, I think I used 58 on 105. So let's see what that says. An irreducible birth. So if you turn to page 105, it says an irreducible birth-death process is transient if and only if 51 holds. And positive recurrent if and only if 56 holds. And there's no recurrent if they both hold, if they both fail to hold. Okay, so that's a nice statement. Let's see if that translates to this. Yeah. Okay, so let's write down those two statements and go from there. I'll flip the page here. So summarizing what I just said, on page 105, 104, it says a birth-death process is transient if and only if 51 holds. So it's transient. We're talking about a birth-death process. Is transient if and only if this thing, mu1, mu x, lambda 1 to lambda x, x going from 1 to infinity, is less than infinite. And then it also says it's positive recurrent. So the birth, death process is positive recurrent. If and only if and that's if and only if 51, no, that's not 51. If and only if 56 holds, and 56 says this. Lambda 0 to lambda x minus 1, mu 1. And this is mu x. Where x goes from 1 to infinity, if this is finite. Okay, so if this series, this is coming from the stationary, I believe. And so if this is finite, then it's positive recurrent. And if, make sure I got that right. Positive recurrent if and only if 56 holds. Yes, that's right. So it's positive recurrent if only that happens. And it's transient if this happens. Now with that information, let's go back to 17. Okay, so it's telling us to look at the gammas. The gammas are what's going on in here, right? It's mu1 to mu x, it's lambda 1 to lambda x. And it says show that if the sum of the gammas is infinite, yeah, well, that sort of follows from this, if we believe this, okay, because part A, if it wants us to show if this sum from gamma equals, or y equals 0, the infinity of gamma y, but the gammas are just these guys again. Well, almost. So what does this look like? It looks like this plus mu1 over lambda 1 plus mu1, mu2 over lambda 1, lambda 2, etc. They want us to show in A that if this is infinite, then rho x0 is equal to 1 for all x. Well, for they say for x greater than or equal to 1. Okay, but but that follows directly from this. Why? This sum if this sum is infinite, this sum is the same as this sum, except maybe the first term is missing, perhaps, the one, but it doesn't matter. Because if this sum is infinite, then the sum from here onward is infinite. And if that's not, if that's, make sure I got this right. If that's infinite, then this will not be true. And if that's not true, then it's not transient. And if it's not transient, that means it's recurrent. And that's what this means. So I think you can deduce this from what they already gave in the text, if you're willing to believe that. Half of it we did. We did this one using this stationarity. So when we found the stationary distribution for the birth death, you needed this series for it to be stationary. Pardon me, you needed that sum to be finite. This one I don't remember doing offhand, but I know we did it back in chapter 2 for what? For chains where P's and Q's were used instead of mu's and lambdas and mu's. So if we assume this, and if we get to assume that this infinite series is going off to infinity, then that implies this infinite series does not converge, because the terms of this are the same as this except for the first term. And convergence doesn't matter what the first term is, it either converges or not, regardless. So if this is infinite, then this one will be infinite. If this is infinite, according to this, the chain will not be transient. If the chain is not transient, then it's recurrent, and then this condition holds. So that would be one way I deduce A from what they've already got in the text. What about B? By the way, I don't think this would be the kind of problem on the test. So maybe I should say that before I even go on to B. Why? Because this is sort of like a proof kind of situation, and it's assuming some things that are above. What I'd be more likely to give you on the test is give you something with mu's and lambdas and ask you whether it's got a stationary distribution or not, or whether it's null recurrent or not. That would be more likely to be on the test than this kind of thing. But since I'm almost done with it anyway, I might as well finish it. We've done A, what about B? Show that if mu is, where are we? Yeah, show that if this infinite sum of the gammas is finite, then rho equals this. What do we think about that? That one is a little harder, because what we'd have to do when you're figuring out rho, you have to figure out all the ways you can get from x to 0. And you'd have to know what they're asking is to show it's equal to this. I think that's harder, but I'm not going to worry about it because it's not going to be on the test. Okay. Let's move to the last problem. The last problem is 2. So problem 2 is more likely to be on the test, or some form of it. Problem 2 looks like this. No. So 2 is giving you a birth death chain having 3 states. 0, 1, and 2. And it's telling you that the rates are lambda 0 here is the same as the rate of mu2. And it's birth death, so this would be typically lambda 1, and this would be typically mu1. And it's telling you that these both are the same. So if you want, you can call this lambda 0. And what is it asking for? It's asking for P0, 0 of t, P0, 1 of t, and P0, 2 of t, which would be the first row of the P of t, P matrix. So this would be 0, 0 of t, P0, 1 of t, P0, 2 of t. So since it's asking for this, and since we know the sums to 1, if we know this and we know this, we just take 1 minus their sum and get this. So it really comes down to just finding 2 of these. Any 2 would work. I think they want you to use the differential equation approach, but I think I'd prefer to use the other approach that we've been doing. So let me show you both approaches if we have time. So what would Q be? Q would be from 0 to 1 has rate lambda 0. 0 to 2 has nothing, so this would be this. From 1 to 0 would be mu1. From 1 to going up would be lambda 1. So this would be minus the sum of those two. And from 2, you can't get to 0, but you could go down. So this would be the Q matrix. Okay, and so yeah, to do it in general like this will probably be, let's see. Yeah, okay, let's give it a shot. This is the Q matrix. What are we using? We're using that the probability of T can be done this way. Okay, so if we're, I'm tempted just to change this into a numerical example. And I think that's what I did on the sample test. So I think that's more likely to see what you would have on the sample test. I would make these numbers, so maybe this would be 2 and 2 and 3 and 1 or something like that, because then we could actually find out numerical eigenvalues and so forth. But sticking with this for a little bit, even though it's again, the sitting that it's in is not likely to be one of my test problems. Why? Because these are not numerical. They could be anything as long as this rate equals this. But let's see if anything good comes out of this. And then the other way to approach it is just using the equations and see if we can manipulate things. So what do we know? We know that omega 3 could be 0. That's it's always one of the eigenvalues. So that means this thing becomes this. What I think I would need now is to find the other 2 eigenvalues. And I'd have to find them in terms of the unknowns that are remaining. And though I can do that, I don't think I want to do it because it won't be on the test again, not in this form. Okay, I'll indicate how it could be done, and then I'll leave it there. So if you're trying to find the eigenvalues of Q, what do? You take Q, you subtract I, xi from it, you take the determinant of this and set it equal to 0. That's fine. You can easily, so that would be finding the determinant of what? Minus lambda minus x, lambda 0, 0, mu 1, minus whatever this is, lambda 1 plus lambda 2, lambda 1 minus x, lambda 1, 0, this, and this. Okay, so we'd have to set this determinant equal to 0 and solve for x. Oh, now that I've written it out this way, it almost looks somewhat doable. Why don't we try to do it and see where we go? So how would you find this determinant? You probably expand along a row or a column. Let's expand along the first row. So it would be minus lambda minus x. And then you cross off the row and the column in which it occurs, and you take the determinant of what's left. That's an x. I'm going to go down the road a little bit until it becomes something that I really don't want to play with. Okay, so that's expanding along the first row. You cross off the row and the column, which occurs times the determinant of this. Then you go to this one. You cross off, you keep the lambda naught. You actually put a minus in front of it because there's a plus minus pattern here. And then you cross off the row and the column in which it occurs, and what would be left would be mu 1, lambda 1, 0, and what? Minus lambda minus x. And then the third entry here is 0 times what you get when you cross off the row and the column having 0, but that's 0 times this determinant, which will be 0. So I think I'm okay. Let me double check. This should be lambda 1, I guess. All right. So with that all said, let's go a little further. So, and this is the determinant of the 3 by 3. So this is set equal to 0. So what's the news? The news is this would be the determinant of this. So this would be minus lambda minus x times the determinant of this. It's not particularly pleasant, but I guess we can live with it. Since everything here is minus and minus, when you multiply, you get pluses. So what do you really got? You really got something that looks like lambda 1 plus mu 1 plus x times lambda 0 plus x. And then it would be minus lambda 0 minus lambda 1. Okay, so that's the 2 by 2 determinant here. And over here, close this up. Minus lambda naught times this determinant would just be what? Just mu 1 times minus lambda naught minus x. Okay, and now we do this all right. We should have a cubic equation. Yes, a cubic equation, but one of the factors would be just be x. And I'm thinking, do I really want to do this? Let me think about it. Well, I see the cubic coming from this one, because this x times this x times this x. And I don't see, this is just giving us a changing some of the lower degree terms. God, I'm really thinking not to continue because this is not a problem I would put on the test in this form. Time-wise, it's going to take a little time and it's not a problem I'm likely to put on the test, so I'm thinking of bailing on this. So this would not be how I would do this problem. Because, why? Because the lambdas and everything are completely general. A problem like this could be on the test where the lambdas and the mu's are specific. So what I said before, if I were to make this equal to 2, and this equal to 2, and this equal to 3, and this equal to 1, such a problem could be on the test. But then in that case, I think it would be much easier to do. You'd be able to find the eigenvalues from your calculator, and they would be numeric, they'd be numbers. And then it would only be a matter of finding the A's, and we pretty much have covered that. Let me give it a little time more, just slightly more. Let's see if we can do it the way they wanted us to do it. They didn't want us to do it this way to begin with, so they wanted us to do it probably the way they did the 2 by 2. So let's look at that. So if we look at that, I'm going to flip the page and try to do it as they wanted us to do it. Let's just see how that works. So advance the page, row some more lines on it, and go for it again. So once again, it's a 3-state guy. This one was lambda naught. This one was assumed to be lambda naught as well. This was assumed to be what? Lambda 1, and this would be mu 1. Okay, so what they would do is what we did. They formed a Q matrix. That part is the same. So lambda naught minus lambda naught is 0. U1 lambda 1 minus lambda 1 plus mu1, and 0 lambda naught minus lambda naught. Okay, so that is the Q matrix. Then what they would have us do is form the forward and backward equations. So that would either be this, that's the forward, or this, which is the backwards. Did they recommend one or the other? Let's see. Yes, they did. Use the forward equations. Okay, so let's follow their advice. The forward equation is this one. So if we were to put everything into this, it would look like this. So it would be that times this. Wow. Doesn't let me keep it. Okay. Since they asked for only the first row, right? So those would be the natural equations to try to write down. So we would get P00 prime of t. This guy would be obtained by taking this row times this column. So we would get minus lambda naught P00 plus mu1 P01 of t. And then this times this is 0. So the first equation for P00 prime would be this. The middle equation would be more complicated. It would be P01 prime of t would be equal to lambda naught times P00. It would be minus lambda 1 plus mu1 times P01. And it would be lambda naught times P02. And then finally, the last equation would be P02 prime would be achieved by multiplying this times the last column. And then you'd have lambda 1 times P01 of t. And you'd have minus lambda naught times P02 of t. Okay, so those are the equations we need to solve. Let's see if we can do something, some grouping of this. So that's what this requires. So there's this, without thinking too hard. Now, let me see. Now let me think a little harder before I get going. This is 0, 0. So if we could, there's two ways to go. We could either just start from scratch, trying to add and subtract these equations together to get something we know how to solve. I mean, something nice happens if I add equation 1, 2, and 3 together, but I'm not sure. I'm looking for some cancellation. For example, if we add equations 1 and 2 together, so let's just label these equations. Call this 1, call this 2, call this 3. If we add 1 and 2 together, then the first term goes away. And if we add 2 and 3 together, then their last term goes away. What happens if you add all three things together? I don't know. Let's play with it. So I'm playing with it a little bit. If I add all 3 equations together, what happens? These two terms cancel. these two terms cancel. So what are you left with? You're left with this term here, U1P01T. You're left with this middle term, is that right? Let me make sure. So this is canceling this. Because they're the same. And this would cancel that. And so what survives? What survives are three terms. What do the three terms look like? They look like this one. And this one. Well, these three, they're all in terms of P01, right? So maybe that's not a bad thing to do. So we have something that looks like lambda 1 plus mu1. And then this minus lambda 1 plus mu1. And then everything is just multiplied by P01 of t. Make sure I'm seeing it properly. That looks like a reasonable thing to do. Lambda 1 plus mu1 minus lambda. Yep, I think that's all fine. Now, how does that help us? The lambda 1s here cancel. Oh, that doesn't help us at all. What do we get? 0? Yeah. So that by itself is no good because we get 0. And over here, well, we actually knew this was 0 already because if you take, without the primes, they add up to 1. So with the primes, it'd be 0 equals 0. So we're not getting anything useful that way. Maybe we should just add 2 together instead of 3. So if we added the first 2 together, let's write down what we get. If we added the first 2 together, we get P00 prime this plus P01 prime of t. And what survived the cancellation here? Well, this and this, but the mu1s would cancel, so you would just get what? Minus lambda P01. It's lambda 1, I believe. And what? And mu1, P01. Let me make sure it's correct. So just adding the first 2 equations together. On the left side, you get that. On the right side, you get, oh, this was still there because this canceled with something else. So if you add these two, these do cancel. This does give you what I have. Minus lambda 1 P0 that, and then this still is there. So this should be what? Lambda 0 P02 of t. Make sure I did it right. Yeah, looks fine. Now the question is it of any use? Well, maybe. So, yeah, but it still has 3 different functions here. It has 0, 1, 0, 2, and 0, 0. we could turn this part over here into 1 minus P02 of t. Well, actually just minus, let's see. So if you add these all together, this equals 0. Because without the primes, it equals 1, and when you differentiate 1, you get 0. So if you added this to this, it's just minus, this should have been 2, if I can read my writing. So I think this is just minus P02 prime. Does that help? A little bit. We have two of the same kind of things together here. So if we wanted to, we could write it this way. Lambda 0 to this. Bring this over. And bring this to the other side. We could try to solve this. This looks like a linear differential equation. P prime, some constant times the same function equals this function. So that's the kind of thing that he's telling us that he gave us a formula for finding. I'm thinking if I want to continue or just try to do this and send you it if I get it. This time is escaping. Why don't I just ask, did anyone get this? Instead of me trying to recreate the wheel here. Did anyone get this to work? Okay, so given that, why don't I do it and send it to you? Or I'll tell you, forget about it, one of the two. But at this point, I think it's probably doable, but I don't think I have the time. But in the meantime, let me close this out by just giving you the answers that I said I was going to give you earlier. So I'll work on this. This is my homework, I guess, since I assigned it. But let me give you the answers to the rest of the sample test, so at least you can check and see whether you're getting those right. I'll just flip the page again. Okay, so on the sample test that I gave you, here are some answers. One A, E00 of T. This turns out to be this. E01 of T works out to be this. P10 T is this. And P11 is this. There's at least two ways to do this. This is just the two-state Markov process. So this is done in chapter 3, and can you just put in what lambdas and mu's are and get these answers from what they have? I think it's on page 92 and 3. So that's one way to do it, or you could do it the recent way we've done it in terms of eigenvalues. Both ways work. Part B. Part B ends up with the following answers. 0, 0 to t. It's very similar looking to what we just had above. 2/3 e to the minus 3t plus a third. P01 of t minus 2/3 e to the minus 3t plus 2/3 and 0,2 turns out just to be 0. P10 works out to be minus 1/3 e to the minus 3t plus 1/3. P11 of t turns out to be 1/3 e to the minus 3t plus 2/3. And P1 of 2 turns out to be 0. P2 0 t works out to be minus e to the minus 5t plus 2/3 e to the minus 3t plus a third. P21 of t turns out to be minus 2/3 e to the minus 3t plus 2/3. And finally, P2 of t turns out to be e to the minus 5t. We went over it pretty much in detail yesterday for those who were able to come to that group session. There were people taping it or recording it, so I think you can get a hold of it if you really need to from classmates. Problem 2 was even faster. Part A was just to write down the forward and backward equations. So this is the backward ones. And here's the forward one. And part B is to find the stationary distribution. And it turns out to be pi. Done by hand. 6/11, 3/11, 2/11. And the ends turn out to all be the same. So part C, M1 equals M2 equals M3. And they're all equal to 1 5/6. Okay, so that's problem 2 on the sample test. Problem 3, I don't think I assigned. Problem 4, I did. 4 is a numerical version. Actually, it's exactly a numerical version of problem 2. So even though I quit on problem 2 and said I tried to do it separately, 4 is doing almost problem 2, but numerically, which is much more likely what you would see from me. So just to give you the example, it's 3 going up here, 3 going down here, 2 and 4. So if you look at that, that is a numerical example that's like homework problem 2 in the book. And if you do all this, the steady state turns out to be oh, it took away my screen, believe it or not. Didn't hide something. Let me see if I can get my note back. Okay, I got it back, but I don't know if you can see it. You can see it now, right? So the steady state and the stationary turn out to be one and the same. And that is this: 4/9, 3/9, and 2/9. And final solution, when you're all done, turns out to be this: P00 of t turns out to be 2/9 e. Oh goodness. It doesn't let me go on. Let me try. All right, so are you back? I assume you're back to the same screen now, but I'm gun shy. Do I have a lot on this page? I guess I have a little bit on the page. Let me just turn the page and do it somewhere else because it's giving me trouble. It's shutting down on me. So I'll turn the page. I'll start a clean page. And let's see if this works now. Without giving me trouble. So I'm on problem 4 still. P00 of t is 2/9 e to the minus 9t plus 1/3 e to the minus 3t plus 4/9. P01 of t is minus 1/3 e to the minus 9t plus 1/3. And P02 of t is 1/9 e to the minus 9t minus 1/3 e to the minus 3t plus 2/9. Okay, so that's 3 of them. There are 6 more. P01 of t is minus 4/9 e to the minus 9t plus 4/9. P11 of t is 2/3 e to the minus 9t plus 1/3. And P12 of t is 2/9 e to the minus 9t plus 2/9. And last, P20 of t is 2/9 e to the minus 9t minus 2/3 e to the minus 3t plus 4/9 and p2(1) of t is a minus a third e to the minus 9t. It's a minus a third e to the minus 9t plus 1/3 and p22 of t is 1/9 e to the minus 9t plus 2/3 e to the minus 3t plus 2/9. Okay, so that's the answer to 4. 5A, I'll give you that. 5A was something we did. And the answers are P00T is e to the minus t, P01 of t is t e to the minus t, and P02 of t worked out to be 1 minus t e to the minus t minus e to the minus t. And then 5B, which I told you not to worry about, but just in case you did, I'll give you the answer one more time from what I did in class. Or I didn't do it in class, I just gave it to you. P00T works out to be 2/3 e to the minus 3/2 of t cosine of square root 3/2t plus 1/3. But this one you shouldn't worry about because that involved complex eigenvalues and you won't see that on the test. I think that's what I did yesterday, mainly. I don't remember if I got any further. I don't believe so. So I hope these 2 pages are helpful. I've got to run. But if you get stuck and you want to contact me, feel free to, as I've already said. I'll see what I can do with problem 2 if I give it more time. Take care.
Hey, bye, Professor.
Yeah,
Thank you. See you next week.
sounds good.